Hey there, tech enthusiasts. Today we're diving into the fascinating world of data structures, starting with the singly linked list. Ready to unlock some coding magic? Let's get started. So, what exactly is a singly linked list? Imagine a line of people holding hands. Each person represents a node, and the hands holding represent the connections, or links between the nodes. In a singly linked list, each node holds data and a reference or link to the next node in the sequence. Now, why do we need linked lists? Well, linked lists are a fundamental data structure that allows us to efficiently manage collections of data that can grow and shrink dynamically. Unlike arrays, linked lists do not have a fixed size and can easily accommodate varying amounts of data. Let's break down the structure of a node. Each node typically has two main parts. Data, this is the value or information the node holds. Next, this is a reference to the next node in the list. The data part can be of any data type, such as an integer, string, or even an object. The next part is essentially a pointer that holds the memory address of the next node. Let's see how a singly linked list works. Suppose we have a list of numbers 10, 20, 30, and 40. Each number will be a node, and we'll connect them in sequence. The first node is called the head, and it's the entry point to our list. From the head, we can traverse the list by following the next references until we reach a node with no next reference, known as the tail. Let's take a deeper look at the traversal process. Imagine walking through a hallway where each door leads you to the next room. You start at the head, first room, and keep moving through doors nodes until you reach the end. There are several key operations we can perform on singly linked lists. Insertion, adding a new node to the list. Deletion, removing an existing node. Traversal, accessing each node one by one. Search, finding a node with a specific value. Let's explore these operations in more detail. Insertion can occur at various positions in the list, at the beginning, at the end, or at a specific position. Inserting at the beginning is the simplest. We create a new node and point its next reference to the current head. Then we update the head to be this new node. Inserting at the end involves traversing the list to the last node and updating its next reference to the new node. Inserting at a specific position requires traversing to the desired position and updating references accordingly. Deletion, deleting a node requires us to update the next reference of the previous node to skip the node to be deleted. For example, if we want to delete the node with value 20, we update the next reference of the node with value 10 to point to the node with value 30. Edge cases include deleting the head node, which involves updating the head to the next node, and deleting the tail node, which requires finding the second to last node. Traversal involves visiting each node in the list, starting from the head and following the next references until we reach the end. This operation is essential for many list operations, such as printing all the elements or checking for a specific value. Let's explore a traversal example where we print all the elements in a list. Searching involves finding a node with a specific value. We start from the head and traverse the list, comparing each node's data with the target value. If we find a match, we return the node. Otherwise, we continue until the end. Searching can be useful in various applications, such as finding a specific task in a to-do list. Now, let's talk about where singly linked lists come in handy. Here are some common applications. Implementing stacks and queues, singly linked lists provide a flexible way to implement these structures. In a stack, elements are added and removed from the top, while in a queue, elements are added at the rear and removed from the front. This dynamic nature makes linked lists an excellent choice for these data structures. Dynamic memory allocation. Linked lists help in efficiently managing memory in systems by allowing dynamic allocation and deallocation of memory. This is particularly useful in applications where the amount of data changes frequently. For example, in a music player, linked lists can manage the playlist, allowing songs to be added or removed easily. Undo functionality in applications. Many applications, such as text editors, use linked lists to remember a sequence of actions. Each action is stored as a node, and the list can be traversed in reverse order to undo actions step by step. This allows users to revert to previous states easily. Graph adjacency list. Representation. Linked lists are used to represent graphs in many algorithms. Each vertex in the graph has a list of adjacent vertices, allowing efficient traversal and manipulation of the graph. This representation is useful in various applications such as social networks and mapping systems. Of course, no data structure is perfect. Let's weigh the pros and cons of singly linked lists. Advantages: dynamic size. Linked lists can grow and shrink as needed without the need for reallocating memory. This flexibility is particularly useful in applications with varying data sizes. Ease of insertion / deletion. Adding or removing nodes is straightforward and does not require shifting elements, as in arrays. This makes linked lists ideal for applications where frequent insertions and deletions are required. Disadvantages: no direct access to nodes. To access a specific node, we must traverse the list from the head, which can be time-consuming. This can be a drawback in applications requiring frequent random access, extra memory for storing references. Each node requires additional memory for storing the reference to the next node, which can be a drawback in memory-constrained systems. Let's look at a real-world example to see singly linked lists in action. Imagine a simple to-do list application where each task is a node in a linked list. Adding tasks. When we add a new task, it becomes a new node that is linked to the previous task. This allows us to dynamically grow our to-do list as new tasks are added. Completing tasks. When we mark a task as complete, we remove its node from the list. This involves updating the references of the surrounding nodes to maintain the list structure. Viewing tasks. To display the to-do list, we traverse the list from the head and print each task. This allows users to see all their tasks in order. To wrap up, singly linked lists are a fundamental data structure with versatile applications. We've explored their structure, how they work, and the operations we can perform on them. We've also seen real-world applications and some advanced variations. Singly linked lists form the backbone for more complex structures and algorithms, making them an essential topic in computer science. Whether you're implementing stacks and queues, managing dynamic memory, or representing graphs, linked lists offer a flexible and efficient solution. We hope this deep dive has been both fun and educational. Thanks for watching, and keep exploring the amazing world of data structures.